We have Ken Smith next. Ken is an old school hacker and dabbler in too many things and wants to show you how to stop manually dereferencing volatiles. That's 15 minutes on how to stop doing something, because it must be pretty hard to stop.
Okay. Oh, it's there first. Screensaver. Okay, yeah, Linux, so. Good to go? Okay, so you probably guessed where I work. This isn't something that we do there. But when I talk about hardware registers, I'm talking about memory mapped I/O or memory that isn't for storage. When you write to it, you're doing something to the hardware. When you read from it, you're reading some status or whatever. And this is the tried and true method. Everybody has seen this. If you've done memory mapped I/O, you treat some arbitrary number as a place in memory. You know where that is because your data sheet tells you where it is. Then you make it a volatile, and then you write to it. Your compiler is going to generate decent code to find that spot in memory and load this new value in. And when you dereference it and read from it, then you get the value. This has a couple of drawbacks. One of them is it looks like a write to memory, because that's kind of how memory mapped I/O is supposed to work. The simplification is you can treat hardware like memory, but the sort of thing that you lose is the sort of volitional aspect. When you write to something, you're actually kind of calling a function in hardware, and when you read from it, you're kind of calling a function that's got a return value. But it's super common and everybody understands it. And so it's hard to break these old habits, especially in embedded systems where things live for a long time and code bases can last forever. So here's one solution the industry has come up with, and I've seen this in the wild. You have bit fields, and so what this gives you, it doesn't solve the problem of writing to a register looking like a write to memory, but what it does solve is treating the individual subcomponents of a register with a named accessor. So when you want to enable the thing, the device that you're talking about, when you want to set a flag on that thing, you can actually call it a flag or an enable. And this is definitely a step in the right direction. This definitely has some advantages. It reads well, it performs just as well, and sometimes the compiler can generate even better code because you're not dealing with the entire register. You might be just dealing with a byte on the end. But it requires that your compiler do the right thing. It might align things wrong, so you need to know exactly how your compiler is going to implement that bit field with the packing and all of that jazz. So here's the sort of shell of the proposal. The thing that I want you to see here is that we have a bunch of template parameters which correspond to things that you know about your register at compile time. You know where it is. You know where within the word it is. You know how many bits it is. And then this mut-t, I call it a mutability policy. You know how it behaves. You know if it's write only, read only. You know if it needs some special handling. And then in this shell, we're just going to talk about read and write, but you could, of course, do more things. And here's how read looks. It just defers to the mutability policy. So whatever class you pass in has to have a read, which implements an interface that looks like this. Generate mask just takes that offset in width and makes a mask at that spot. And that's a const expression. It used to be a template meta program, but happy const expression can solve this. Write is similar, it just defers to the mutability policy. It has a parameter, so we give it the value. And this is an example mutability policy. It takes the device, it takes the offset and mask, and it just does something very similar to what we did when we were dereferencing volatiles. Why is this useful? You might notice that we in this read-only policy, we don't have a write function, and of course, because this is going to be duck-typed, you call register write on a read-only register, and it's going to give you a compile time error. So this is a little bit of safety that we can build into our register access. And this is how it looks. In this case, I'm using a write-only register. We're writing to the register is defined as at FFFF 0000, and it's left shifted one off the least significant bit. It's one bit wide, and when we write to it, we're writing to it. We're saying I'm doing something to a thing. I'm not saying I'm writing some value to a piece of memory. It's a little bit more volitional. It kind of captures a little bit more about what you intend when you write to a memory mapped I/O register. And again, here, since this is write only, we can't read from it, and that's a piece of safety. And most of the time, when you're dealing with memory mapped I/O, it could be safety critical of a car or some kind of medical device. So here are a couple things that I like to point out. Not only is it's volitional, it's safer, and you can easily translate what you're seeing in the data sheet to what you write in the code using namespaces to say, okay, this peripheral has this register, has this field, and you can have that look like the data sheet as much as you want to go there. And the mutability policies provide an interesting opportunity which none of the other techniques can give you. And that is, you can add more stuff to them. You can log register access. You can mock out the registers for your entire chip and run a desktop version of your application, and all sorts of other interesting things. The one requirement is that you optimize, because if you don't use optimization, then all of these static function calls are actually function calls. But if you use optimization, they will all go away and become inlined. You can find a little bit more about this here, including a living example that shows you the disassembly of what these look like. All of them perform about in the same ballpark, 4 or 5 instructions for a write, 2 or 3 instructions for a read. And if you want to discuss it, you can email me here. Thanks.